I see most of the people logged on. Any questions from last week while we're waiting to see if the last couple of people log in? We're only a little ways into the intermolecular forces chapter. We've got a ways to go on that.
So I'm trying to open up the chapter notes. And each time I try to do it off of pages, it just says unauthorized. I'm not sure if anyone else has come across that, or I've tried it on a couple computers.
I had that issue. That's where you had to email it to me and
For notes or for homework?
For notes, I was able to access the homework.
Yeah, that's the issue I have.
Weird.
They say it's not a Canvas problem.
Because they're the same kind of, it's like, I use the same program and the same file style to upload homework to the modules that I do to the pages.
Yeah, it's weird because I was able to open all of the other notes. It's just that one I can't get into.
The person I spoke to in Canvas support said that the link could be broken. So I don't know if you're able to delete it and then re-upload it or upload it elsewhere. But they said it could be a broken link.
Let me scrunch down my screen and see if I can do an edit function and reload them. Maybe that'll help. I'm not sure. Give me a moment. All right, so what I told Canvas to do was delete all of them, although I didn't delete the page, And then I reloaded organic and the little itty bitty coordination compound one and intermolecular forces and solutions. All I did was reload all of the files that I already had there. I don't know what that'll fix the problem or not. So here's a piece to the puzzle that I have no control over. From my end of it, the posting of files functionality used to be this little set of bars on the right-hand side of the page, and it would say upload image, upload file, upload something. I forget what the last one was. And then I would upload it from my computer and then tell it to post it. All of that has gone away. Okay. They didn't tell me that. I just this was like about a week or so ago. I was tinkering with stuff to just put some more stuff up on the page because I'm trying to stay ahead. And now that they have this entirely different setup where I do edit and then it just gives me a box and then I have to hit insert. And after I hit insert, it it's not really it's sort of a drop down, but not exactly. And it pops open and then it asks me what I want to do. So I go upload documents. I don't know if them switching, okay, they keep doing this in the middle of the semester, which makes me furious. It's like, if they're going to do stuff like this, they really need to only do it in between semesters. Because I'm wondering if somehow that is a piece to the puzzle of things not working, but half the time. Yeah, I don't know. This is just sort of my guess. My tech skills are sort of but yeah, they keep changing stuff in the middle of the semester. It's kind of ridiculous.
So it's opening just fine for me now.
Yeah, it works.
Okay, so maybe it has to do with when I uploaded them before, it was with their previous system. And now that I re-uploaded them, I used the new system. Like I said, it's kind of sort of like a little itty bitty drop down. It like pops open and then gives me this little set of boxes over to the right hand side, which I'm sure you guys don't see because that's a teacher function. Yeah, I don't know why it like screwed it up, but hopefully, yeah, keep me in the loop if you have trouble opening stuff. Oh, and somebody just has to be logged in and my brain, my thing went weird. All right. The whole thing is being flaky now. Gallery view. No, I don't want gallery view. I hate this when I click something and then it like changes the way I'm like looking at stuff. Arg. Ah, there. Okay. All right. So hopefully maybe that will fix, at least for the moment, connectivity issues for the files that I've already loaded. So yeah, I don't know. We'll kind of keep an eye on that. Some of you I will see tomorrow for lab. I usually get to campus about 4:30. Lab starts at 5:30 because we were trying to make it so that all the night classes start at the same time when we're doing this weird hybrid thing. So if you have questions that you would like to ask in person, I will be in the lab, the one that's up next to the bathroom, the one at the far end of the hallway, about 4:30-ish if you want to come on by then, if you have stuff you need to ask me. Otherwise, class actually starts at 5:30. All right, let us dig back into intermolecular forces. All right, so the last thing that we were talking about was London dispersion forces. And I just realized why it's telling me I've done this wrong, because I left the I out of dispersion. London dispersion forces, when we were talking about them last week, they're pretty wimpy. When you have this situation where non-polar molecules such as hydrocarbons or noble gases, which under most circumstances are also very non-polar, you can kind of shift their world around a little bit and create some oh so very temporary dipoles. So this is kind of the last thing we were looking at, especially in terms of noble gases here. The idea that if you kind of swish everything over to one side, this will actually give you a level of polarity. You get so that one side is somewhat positive and one side is somewhat negative. Doesn't last very long, which is definitely why they are at the bottom end of the energy chart there with all the interactions. So let's look at two molecules that actually share a lot of similarities. We have a bromine molecule, one that has two Br atoms hooked together. And then we have another molecule that is also two atoms, but it's two different atoms. We have iodine and chlorine. So if you actually were to look up numbers off the periodic table, you would find out that both of them have the same molecular weight, give or take about a tenth. And both of them have the same number of electrons in the molecule. But we have some differences on the physical characteristics end of things. Bromine melts at negative 7.2 Celsius. Iodine monochloride, on the other hand, melts at about room temperature. 27.2 on the Celsius scale is kind of warm room temperature. Why? It is all about the polarity. Back to electronegativity. If you have two identical atoms, such as your Br2, except for London dispersion, you're not going to get any other polarity forces going on. But the iodine hooked to the chlorine, there's a moderate amount of electronegativity difference, which gives you a polar molecule. That is definitely going to influence how they are attracted to each other. If you have two ICLs sitting next door to each other, you're going to get a little bit of attraction. The iodine from one molecule can also be attracted to the chlorine of its buddy as well as its own chloride atom. So this interaction causes attractions between the separate molecules, which actually influence physical and sometimes chemical properties. So let's look a little bit more specifically at some liquids. Liquids do some things that solids and gases don't. Those particular things are surface tension and viscosity. So surface tension, little buggy things. Sometimes they call them water striders. I've heard them call some other things too. And they kind of step their way across the surface of a pond, and you kind of wonder, why don't they sink? Also, if you lay a needle on water. Okay, not pointy end down. We're talking horizontal on water. And it also has to be not a super enormous needle. Think kind of average, I'm going to mend my pants sort of needle. I quilt a lot. Okay, so I always have lots of needles laying around my house that are only about an inch and a half long. They have a diameter of about 1/2 to 2/3 of a millimeter. That's kind of what we're looking at here. Both of those things, both the bug and the needle, are more dense than water. From a sheer density comparison, they ought to sink. They don't. So let's take a little bit deeper look about what surface tension is. So from a physics point of view, we're going to address it as the resistance of a liquid to an increase in its surface area. Now, there are certain ways that you can compare this. One of them involves a equation that I presented here. We're going to, in just a second, look at the picture that goes with it. The little squiggle out in front there is a gamma, and it is equal to force over 2L. That's actually supposed to be an L, not a number 1. So F is force, which in the world of physics usually means newtons. Length of the bar actually relates to this little gadget thing that they use. All right, let's scroll down here and look at the picture a little bit better. I always think of it as looking a little bit like a paper clip that has a slidable bar to it. So we have this little square frame, and it's small. Okay, we're talking like a few millimeters tops. And you have this little device that pulls on this slidable bar. This is where F is. The L is how wide the slidey is. And I kind of like this picture because it gave you this little side-on view. I actually thought that was a really sort of useful way to kind of give you 2 different versions, top down and sort of side on, as a way to do this. So surface tension for water, not that you need to know the actual number value, but just to give you an idea what we're talking about here. Surface tension for water at a fairly room temperature, 71.97, note it's 10 to the negative third, so we're dealing in thousandths at this point, newtons per meter. So to give you some comparisons, water is one of the things that has one of the higher surface tensions. This is also why, for instance, if you are pouring water, say from a cup into something that is maybe sitting on the counter, you can pour it and the water has a sort of stuck together sort of cohesion property, and it makes a relatively, coherent stream. So other things, hydrocarbons, for instance, have much less surface tension and don't pour with the same sort of ease. They splatter a lot more. So here's some ways to kind of approach this idea. So take a look at this little picture here. We've got the air and liquid interface here. And if the water molecule is down inside the water, okay, so it's being pulled up and down in all directions sideways. If you have a water molecule that's actually up near the surface, see the 2 little dotted circles, okay? So the force is being pulled downward, to its buddy neighboring water molecules and side to side, but it's not being pulled up. It kind of, sort of generates a skin in terms of the forces that are attracting to each other and not to the air. This is also why it hurts when you belly flop, okay? Because you are hitting the surface tension of the water flat on, okay? More thoughts on this. For instance, if you are a cliff diver, okay, you can potentially, I don't know why anybody would want to do this, I don't know, but you can dive 100 meters, sometimes a couple 100 meters from the cliff down into the water. But think about how the diver is shaped. The diver is long and pointy with hands overhead and body at a perpendicular angle to the surface of the water. Hence, you go pretty deep, and so hopefully you're diving into an area that's very deep when you're doing that sort of thing, but you can do it without getting hurt. On the other hand, if you jump off the Golden Gate Bridge, chances are if you did that, you don't have cliff diving skills, and you kind of spread your body out as you flail, falling downward. And when you hit, it is very bad because you splat. So there's some other things that tie into this idea. Well, what if there was nothing to attract those coherent molecules underneath? Hence, they would form a sphere. If you are on the International Space Station, your coffee cup is not allowed to not have a lid, because the coffee would float up out of the cup and form a bubble, a sphere, okay? Why? Has to do with surface to volume ratio, okay? If you want to pack the largest amount of volume with the smallest amount of surface area, the geometric figure that does this best is a sphere. So this gives you roundness to things that have less gravity exerted on them. Even if you do have gravity, there is a certain amount of two opposing forces, okay? They influence surface tension, but they also influence capillary action. If you are familiar with what a capillary tube looks like, they are sometimes used in medicine. They're about as long as your finger, and they have a diameter of about 1 millimeter tops. You can use them for testing certain blood qualities by poking your finger, and you have a drop of blood, but once you touch the capillary to the drop, it kind of slurps it up into the tube. All right, this is all based upon these two main concepts. We've got cohesion. Cohesion means it wants to stick to itself. So you go out and wax your car, you spray it off, all those water beads that are left are trying to form little spheres, but granted, there's some gravity involved here. So they're not perfect spheres, but they are nice, round, usually half a sphere. Adhesion, on the other hand, is sticking to something else. Makes me think of the Bounty paper towel ads, where you stick the corner of the paper towel in the puddle and it kind of slurps the puddle up into the paper towel. This is all about adhesion. Okay, the idea that different things are attracting each other. One more little piece to the puzzle is surface tension can change with temperature. Now, granted, if you decrease your temperature enough, you actually reach the point where whatever your liquid is, it will eventually become a solid. Obviously, with water, we're talking about 0 degrees Celsius, because if you're at 1 degree Celsius, it might be cold, but it's still liquid. If you hit 0 degrees Celsius, now you've got an ice cube, and hitting the ice cube would definitely hurt. On a purely conceptual note, we'll call it, you will sometimes run across odd mentions that indicate solids have a kind of a surface tension. Just kind of, okay, random trivia, just kind of know that the two things are not incompatible. It's just way more difficult than approaching surface tension from a regular point of view. All right, let's switch gears a little bit to the other type of liquid property, which is viscosity. Viscosity probably makes you think of oil commercials. More fun Greek letters here. We've got an eta, kind of looks like a letter N that somebody tried to melt. On the top of your little fraction there, that cursive looking letter T is actually known as a tau, T-A-U, and it's over a derivative, du-dy. So what does this give you? What you're doing is you are comparing shear stress to rate of strain. Okay, pieces of this puzzle you need to think about. All of this has to do with how much attraction, okay, we're going back to the cohesion adhesion thing here. How much attraction is there between the thing that you are measuring and itself? So for instance, if you have water flowing through a pipe, the water interacts with itself, but the water also interacts with the pipe. So you have this sort of comparison thing going on. It is also temperature dependent. Higher temperature gives you lower viscosity. Lower temperature gives you higher viscosity. So the whole, warm molasses flows faster than cold molasses. In all of my massive amounts of cooking that I do, I usually keep honey in the house for a couple of recipes that I like. Once winter rolls around, sometimes getting it out of the bottle is a little harder, so usually I nuke it because then it's more liquidy and easier to pour out of the bottle. And I was looking for a visual to kind of show you, and I kind of like this little table here because it just gives you some thoughts on how viscosity compares. So obviously, air is not very viscous because we breathe it. Acetone, which we saw a little bit of as a ketone in the organic chapter, acetone is not very dense. It's also not very viscous either. Methanol, the smallest of the alcohol molecules. So meth means it has one carbon. And then you get to water. water is considered to be kind of the standard comparison in so many things. We use it as a comparison for density. We use it as a comparison for viscosity. We use it as a comparison when we start talking about boiling. So water is one. Ethanol, while its density might be slightly less, its viscosity is slightly more. We're treading on that intermolecular forces point of view. Then we get into things that are a little more obvious as being thicker. Olive oil, motor oil, maple syrup, and then we get honey, and at the far upper end we get molasses. You could also, and we'll kind of circle back to this later, you could also talk about glass. Okay, I know that probably provokes kind of a head twist. You're going, but glass is a solid. Yes and no. When we get to the end of the chapter, we will talk a little bit more about the fact that on an absolutely bare bones physics point of view, glass is a liquid because it is amorphous. So if you have old hand-blown glass windows, and you were to take a caliper and compare the thickness at the top of the window and the thickness at the bottom of the window, you would actually find that it's a little thicker at the bottom of the window, because over years, literal years, you get a little bit of flow, kind of like a glacier. All right, we're going to switch from liquids back to solids for right now. And two big categories, like I said, glass kind of keeps popping up here again. Glass being a solid, just barely at this point. The other major type of solid being crystals. And crystals are the ones that we are going to pay the most attention to. We've got the idea of crystals have shapes. We are going to refer to them as a lattice. So lattices not only are like that thing in the garden that you grow roses on, or a pie that have the strips that overlap. They also apply to crystals. So if we look at the tiniest unit, we are going to refer to this as a unit cell. So I provided you with a list, but here in just a second, we're going to look at the pictures. So they are known as cubic, tetragonal, orthorhombic, rhombohedral, monoclinic, triclinic, and hexagonal. So those are the names. Now let's look at the pictures. All right. So the top row is the ones that are cubic. And in the grand scheme of things, they are the ones that we are going to pay the most attention to, but we do need to touch on the other ones. So the first one, first left-hand one there, little square box, 8 atoms in a perfectly symmetrical box. Then we hit the next one that is known as body-centered. And I often refer to it as ping pong ball in a box. Then we have face-centered. If you had a die, as in like one of a dice, and it was defective, and instead of having 1, 2, 3, 4, 5, 6 dots on each side, if every side had one dot, like I said, defective dice. This would be what a face-centered die or face-centered cubic cell looks like. We're going to touch just momentarily here on some of the other ones. When you look at the tetragonal one, what they are dealing with here is that one of the sides, well, actually not one of, two of the sides, back and front, are rectangular. And we kind of twisted it off to one side a little bit. Okay, now they refer to it as monoclinic. Look at the next row down. What if top, bottom, and side were rectangles and the front was still a square? That's called orthorhombic, and it has these kind of variations on a theme, same way the cubic does. We've got a body-centered one, we've got a face-centered one, we've also got an end-centered one. That one seems to be peculiar to things that have rectangular faces, because we see it in the monoclinic and we see it in the orthorhombic. There's rhombohedral. Basically, all the faces are a little bit diamond shaped. Hexagonal, so top and bottom, are hexagon shaped. And then we've got the triclinic, which again is sort of like rhombohedral, but it's a little bit more elongated. So we're going to mostly pay attention to just the top row, but the other ones you do need to be aware exist. They are alternate things. And if perchance you take geology as a different science to fulfill whatever your degree criteria are, you may actually encounter some of these other types of unit cells, because there are certain types of minerals which tend to give particular types of shapes. The book also talks a little bit about X-ray diffraction, on the idea that this is sort of how they got there. Okay, if you have some really nice expensive machinery, which is known as an X-ray photometer, you can do X-ray diffraction to look at things on a level that gives you information about the way that atoms are arranged. More useless trivia. I have a buddy who lives in California who started out his career as an environmental chemist. And he was doing some X-ray diffraction for the project that he was working on. And X-ray diffraction sometimes involves dissolving your samples in hydrofluoric acid. Hydrofluoric acid, HF, is unbelievably nasty stuff that if you get it on you, sometimes will not stop eating until it hits bone. In fact, that's the way you treat burns for hydrofluoric acid, is you pour a calcium-based product, usually something like calcium chloride or calcium hydroxide, onto the burn in order to neutralize it. Well, he was in the lab actually by himself, and he cracked one of the containers that he was dealing with and got a few drops on his clothing. And to hear him tell it, he said, "I have never been naked so fast in my life." He ripped off all his clothes and jumped in the safety shower to make sure that none of it had actually come in contact with him. So yeah, just things that happen to chemists. So let's go back to the cubic cells here, because like I said, they are the ones that we are going to pay the most attention to. I don't like the picture for the face-centered one. It looks, because they have it in pink and yellow, something about the way they drew where the pink ones are for the face-centered makes them look like they're weirdly in line with each other, which is not true. I like the pictures further up the page for the face-centered one. It makes something about the visuals works better. So one of the things that we are interested in terms of the cubic cells has to do with space and also has to do with how many atoms we are considering, because it makes a difference. So as we're progressing through this, just to give you some more ideas about things that sort of have a little bit of real world application to them, things that have lattice structure that are ionic solids. So table salt, sodium chloride. If you have a medium powered microscope, something that doesn't give you, like 10,000 magnification, something that gives you a couple hundred magnification, you can really easily see the cubicness of the salt crystals. Molecular solids also make crystals. They're just not ions, things like sugar, sucrose. But there are other things that are atom-based. In other words, they are not part of a larger whole except in their lattice structure. Buckyballs and diamonds. If you are not familiar with buckyballs, about 15 years ago, a Nobel Prize was awarded for the creation of buckyballs. If you can imagine a soccer ball on the subatomic scale, where every little corner of the hexagons that make up your soccer ball is a carbon atom. And so you end up with this ball that has a lattice structure that is shaped like a soccer ball. And the reason they're called buckyballs, Buckminster Fullerene was an architect from the 60s who built geodesic domes as part of his architecture. And so calling them buckyballs is sort of a nod to that particular person because of the way they look. All right, more pieces to this puzzle. Packing efficiency. How much stuff can you put in space? How much stuff can you put in a small space? How much of the unit cell is actually atoms? This is sort of hypothesizing that atoms are basically round versus how much is empty space, okay? Somebody hands you a crate of grapefruit, okay? Grapefruit are basically round. And even if you stack them in a crate, which is somewhat rectangular, there's empty space because since the grapefruit are round, you've got a layer, and even in the layer, they're all kind of a little bit of empty spaces. And you've got another layer on top, and so there's empty spaces vertically as well as empty spaces horizontally. So we're going to call this closest packing efficiency, and this is how they calculate it. You compare the volume of your spheres to the volume of your cell. This is assuming that your cell is cubic. And since it's a percentage, we're going to multiply by 100 at the end. So if you took, okay, and this is actually not supposed to just be zeros, this is supposed to be a little picture. I didn't redo this when I was doing my notes. If you took two circular atoms and you kind of snuggled them up next to each other so they were actually touching, the distance along the edge would be 2r, r meaning radius. So from the center of the left-hand one to the center of the right-hand one is 2 times the radius. We're just going to use the volume of the sphere geometry value here, 4/3 pi r cubed, because that's how you figure out what the volume of a sphere is. And we compare them. So if A in this case is the designated letter of the alphabet that they like to use for the length of one side of a cube. And we're going to compare that so that we have volume of spheres versus volume of cells. So if you have a simple cubic one, this is the one that had just the 8 atoms where everything's on a corner and there's nothing in the middle. So it's actually kind of a crappy way to package things that are round, because only 52% of the space is actually atoms. The other 48% is empty. If you do body-centered BCC, body-centered cubic, you get 68%. So, ooh, getting better. However, face-centered is actually the best option. If you do them from a face-centered point of view, you actually get a packing efficiency of 74%. It is the most efficient way to put round objects in a square space. Okay. This helps us in the long run also understand the relationship between side length, because remember I said side length is the letter A, versus R, which is the radius of your atom. So it actually kind of depends upon which version of the cubic you've got as to what your relationship is. So when you do the simple cubic one, SCC, that one's the most straightforward one. The length of the side, A, is just 2 times the radius. I couldn't get my Microsoft Word to give me the top of my square root symbol, so it looks kind of wonky there on the next one. BCC, body-centered cubic. The side length is 4 times R over the square root of 3. So if you end up deciding to print your notes, you can go back and put the rest of the little squiggle atop of the square root symbol there for 3. Face-centered also has a square root symbol in it. The side length of A is the square root of 8 times R. Now beware, the square root symbol only involves the 8. The square root symbol does not like bridge across. It's not the square root of 8 times R, it's just the square root of 8, and then you multiply by R. All right, and then we kind of devolve into the math. You really need a calculator that is capable of doing both cubes and cube roots to work on these types of problems. All right, so let's go through a few of them. If you have a body-centered structure, and we know that our atomic radius value, this is my R, is 170. How big is the unit cell? So I need to plug it into one of my 3 equations. This is why you have to know what kind it is. I know that it's a body-centered, so I'm going to use my middle equation there. Side length is 4 times 170, and then divide by square root of 3. So 4 times 170 is 680. The square root of 3, 1.73, etc. Finish your division, and I get 392.6. That is the length of one side. But that's actually not what it asked me. It said, what's the volume of the unit cell? So since a unit cell, for all the ones that we're doing math for, are little cubes, you have to do the value of your side length cubed. This is, remember, not multiplied by 3, cubed. 392 times 392 times 392. This will give me 6.05 times 10 to the 7th. And I didn't change my unit, so right at the moment, I'm still in the unit of picometers. Really small, 10 to the negative 12. All right, let's switch to a slightly different structure. What if you have a face-centered one? Smaller atom, though. This one only has a radius of 36, so maybe it's something dinky like beryllium. What's the volume of my unit cell? Now note, different equation because it's no longer body-centered, it's actually face-centered. So side length A is square root of 8 times R. So I'm going to do square root of 8 times 36, I get 101.8. Then I'm going to cube it. So the volume of that unit cell's a little smaller than a one above. 1.06 times 10 to the 6th. But picometers only has just so much use. Most of the time, we would like to be able to tie this into more useful macroscopic world units. I want to convert it over to cubic centimeters. So look at your conversion here. 1 centimeter is 10 or 1 times 10 to the 10th picometers. There's a 10 order of magnitude difference there. But I'm also cubing this. So I need to cube my conversion factor. 1 times 1 times 1 on the top gives you 1. But 1 times 10 to the 10th times 1 times 10 to the 10th times 1 times 10 to the 10th gives you 1 to the 30th on the bottom. So by the time I do the top line on that page there, and I'm converting from cubic picometers to cubic centimeters, note the number out in front of the multiplication symbol doesn't change. It's still 1.06. It is my exponent that drastically changes here. I'm going from 10 to the positive 6th exponent all the way to 10 to the negative 24th. We are talking submicroscopic here, okay? 10 to the negative 24th cubic centimeters is a dinky amount of space. What if I actually knew how much my little inky dinky cubic cell weighed? I'm going to make it weigh a couple of AMUs. 1.6 times 10 to the negative 23rd. But look at my units. I've got grams and I've got cubic centimeters. That allows me to calculate density. I get density of 15.09 grams per cubic centimeter. I know that some of you had me last semester, so let me kind of rehash this for a moment. When you are talking about density in the grams per cubic centimeter way. There are some benchmarks you need to think of. Unless it is a gas, you're unlikely to have densities less than half a gram per cubic centimeter. If you're talking about liquids, liquids tend to range, okay, not including mercury, liquids tend to range in densities from about a half a gram per cubic centimeter up to maybe a couple of grams per cubic centimeter tops. Solids, the only thing at the sort of upper end of the double digits area for solids is osmium. Osmium being one of those transition metals down there buried in the middle of the periodic table. Osmium has a density of about 28 grams per cubic centimeter. So keeping that in mind, if you're working on homework problems, if you're working on, working on stuff to try to make sure you know how to do it, and you're coming up with something that seems to indicate that you have a density of like 712 grams per cubic centimeter, there's a math error, okay? If you have a density bigger than 30, be really suspicious because you probably did something mathematically wrong. In the units of grams per cubic centimeter, anything above 30 is pretty close to impossible. How about if we go back in the other direction? This one's messy. Ti, titanium. More transition metals. Titanium has a body-centered structure. It's not too terribly dense, though. 4.05. This is why they use titanium in things like planes, because you want them to be strong but not super heavy. I want to calculate the edge length, A, and my atomic radius, R. All right. One more addition to the puzzle. If you have a simple cubic cell, that whole 8 atoms on a corner, the initial reflex thought is people go, well, it has to have 8 atoms. No, because we're gonna slice it. We're gonna slice it such that it's perfectly flat. And remember that since atoms are more or less round, if you slice it in such a way so that you cut each of your round atoms so that only 1/8 of each of those balls is actually inside the box. There's a halfway decent picture of this in your textbook. Nothing in the middle. So 8 times an 8th gives you 1. Body centered. You still got those little 8/8ths, but you've also got the one in the middle. Back to ping pong ball in the box. What about the face centered? So you've got all the ones that are on the corner, which make 1. But each one that's on a face is halfway embedded. 6 faces, 6 times a half gives you 3. There are 4 complete atoms. So like I said, these are pieces you need to think of in doing these types of problems. All right. We are going to assume that our titanium is body-centered. We need periodic table information. If you look up titanium on the periodic table, you will see that it has an atomic weight of 47.88. So right at the moment, we're talking about individual atoms. So right at the moment, we're going to say that the unit is AMUs. So 2 atoms in the box times 47.88 AMUs. But I don't really want to leave it in AMUs. I'd really rather have grams. So here's your conversion unit. 1 gram is Avogadro's number, 6.022 times 10 to the 23rd AMUs over A cubed. So I'm like, I have pieces. I have density. I know something about the mass. I don't know the volume yet. All right, so let's work our way down through the math. Multiply your first 2 bits together there. We get 95.76 times 1 over Avogadro's. We're going to leave the A cubed by itself for just a moment. Finish out everything on the top. We've got density, 4.05, now equals 1.59 times 10 to the negative 22 grams over volume. Do your little algebraic rearrange. If you have one thing on the top on the left-hand side and one thing on the bottom of the right-hand side, you can flop them. So now I've got A cubed is 1.59 times 10 to the negative 2 over 4.05. Divide. Now we get a tiny, tiny, tiny number. 3.93 times 10 to the negative 23rd. And this is why I said you need a calculator that does cube roots, because you have to take the cube root of both sides. Once I finish that bit, my A value in centimeters is 3.4 times 10 to the negative 8th. But I had one more thing it asked me for. It asked me for what the radius was. So back to that whole idea of it's a body-centered one. The other little body-centered piece that you know, A equals 4r over square root of 3. I know what my A is. A square root of 3 is just a number. Solve for your r. Rearrange, divide by 4. If you leave it in centimeters, it's 1.47 times 10 to the negative 8th. If you converted it back to picometers, all you're doing is moving the decimal place. So it's 147 picometers. These are kind of nasty looking equations from the math point of view. But ultimately, this is what you need to be able to do. If you know density, you should be able to, and you know what your element is. That's also key. You have to know what your element is. You can backtrack your way to side length, which is your A value, and R, which is your radius. If they give you A and R, as long as you know whether it's SCC, BCC, or FCC, you can crunch your way forward and figure out what your density is. It's a two-way street. Yes, the math is kind of messy. This is also why college algebra is a prereq for taking college level chemistry, because you got to do a little rearranging and got to keep track of your exponents and all that sort of thing. So all of those pieces go together. I gave you examples. There are also a couple of examples in your textbook. I'm sure that there are some websites. Not everybody does problems exactly the same way, but the equations don't change. The 1, 2, and 4 atoms, the little relationship between the A's and the R's, those don't change. How they set it up and tinker their way through the math might change a little bit if you're looking at other examples, but probably will not change drastically. This gets us about 60 to 70% of the way through this chapter. So we may finish the chapter on Thursday, which would then give you the weekend to do the homework set. We'll kind of see where we end up on Thursday. But kind of, I'm just sort of looking ahead a little bit, kind of estimate that you may have homework due for this chapter a week from tonight. Questions? Some of you I will see tomorrow night in lab. Bye.